Tonight, we're going to talk about something that has astronomers questioning everything they thought they understood about the early universe. On May 16, 2025, the James Webb Space Telescope spotted a galaxy so distant, so impossibly ancient, that its very existence challenges our most fundamental theories about how the cosmos evolved. This galaxy existed just 280 million years after the Big Bang. And by the end of tonight, you're going to understand why this discovery isn't just another record breaker, but a troubling puzzle that threatens to rewrite our understanding of cosmic history. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky and see a star, you're not seeing it as it is right now. You're seeing it as it was years ago, decades ago, sometimes centuries ago. The light from that star has been traveling through space for all that time, crossing the vast emptiness between there and here, carrying with it information about what that star looked like when the light began its journey. The farther away something is, the further back in time you're looking. This isn't science fiction, it's just physics. Light travels at a fixed speed, about 186,000 miles per second. Nothing in the universe can travel faster. So when you look at something 100 light years away, you're seeing light that left that object 100 years ago. You're literally looking at the past. Now, extend this principle to its extreme. If you could look far enough into space, you could, in theory, see all the way back to the beginning of the universe itself. You could witness the first stars being born, the first galaxies forming, the dawn of cosmic structure emerging from the primordial fog that filled space in the early universe. This is exactly what the James Webb Space Telescope was designed to do. Webb launched on December 25, 2021, and it was built specifically to peer deeper into the universe's past than any telescope before it. Its massive mirrors, its infrared sensors, its position 1 million miles from Earth, all of it engineered for one purpose: to see the universe as it was in its infancy. And what Webb has found has been nothing short of shocking. Before Webb began its observations, cosmologists had a fairly clear picture of how the early universe should have looked. The Big Bang happened 13.8 billion years ago. In the first few 100 million years after that, the universe was a relatively simple place. Mostly hydrogen and helium gas, gradually cooling, slowly collapsing under gravity to form the first stars. Those first stars would have been massive, hot, and short-lived. They would have burned through their fuel quickly, exploded as supernovas, and scattered heavier elements into space. Over time, over hundreds of millions of years, those elements would have allowed more complex structures to form. Small galaxies at first, then larger ones as gravity pulled matter together. The universe should have taken its time building up to the grand structures we see today. That was the theory, supported by decades of observations and computer simulations. The universe was supposed to start small and simple, then gradually become larger and more complex. But Webb is showing us something different, something that doesn't fit the models. When Webb first turned its instruments toward the deepest reaches of space, looking back to when the universe was less than 500 million years old, astronomers expected to see a handful of small, faint, primitive galaxies, early structures just beginning to take shape in the cosmic dark. Instead, they found hundreds of bright, well-developed galaxies that shouldn't exist yet. Galaxies that were too large, too luminous, too chemically enriched for their age. Galaxies that looked like they'd had billions of years to develop, not just a few 100 million. These discoveries sent ripples of confusion through the astronomical community. At first, there was skepticism. Maybe these galaxies weren't as distant as they appeared. Maybe dust or other factors were making nearby galaxies look like they were from the early universe. Maybe gravitational lensing, where gravity bends light, was creating false images or amplifying faint objects. These were all reasonable concerns, because if these galaxies really were as ancient as they appeared, it would mean our models of the early universe were fundamentally wrong, and that's a huge problem. Our models aren't just guesses, they're built on decades of observations, experiments, and theoretical physics. They're tested against everything from the cosmic microwave background radiation to the abundance of different elements in the universe, to the distribution of galaxies we see today. If the models are wrong about something as fundamental as how quickly galaxies formed, what else might they be wrong about? So, astronomers designed a survey to find out the truth, the Mirage or Miracle Survey. The name captures the question perfectly. Were these bright early galaxies, mirages, illusions created by dust or other effects that made them look farther away than they really were? Or were they miracles, real objects that somehow existed impossibly early in cosmic history? The survey team, led by Rohan Naidu at MIT, used Webb's most powerful instrument, its near-infrared spectrograph, to analyze the light from these suspicious galaxies in exquisite detail. They weren't just taking pictures anymore, they were breaking the light down into its component wavelengths, looking for the specific signatures that would reveal exactly how old these galaxies were. And in the data, they found their answer. Among all the candidates they examined, one galaxy stood out. They called it MOM Z14, named after the survey itself and its redshift value of approximately 14. This galaxy appeared in images taken on May 16, 2025. At first glance, it didn't look like much. Just a few pixels of reddish light in Webb's camera, easily lost among the thousands of other galaxies visible in the same field of view. But those few pixels contained information that would rewrite record books. When the team analyzed MOM Z14's spectrum, they found something extraordinary. The light from this galaxy had a redshift of 14.44. Now, redshift is how astronomers measure distance and age for extremely far-away objects. As the universe expands, it stretches the light traveling through space. The farther light has traveled, the more stretched it becomes, shifting toward longer, redder wavelengths. The higher the redshift number, the farther away and more ancient the object. A redshift of 14.44 means this galaxy's light has been traveling through expanding space for 13.53 billion years. The universe is 13.8 billion years old. So, MOM Z14 existed when the universe was only 280 million years old. That's just 2% of the universe's current age. To put that in perspective, if the universe's entire history were compressed into a single year, MOM Z14 would have existed on January 7th. Everything we can see around us today, all the mature galaxies, all the cosmic structure, all of it came later, much later. MOM Z14 broke the record previously held by another galaxy discovered by Webb, Jade's GS Z14-0, which existed just 300 million years after the Big Bang. But this wasn't just about breaking records. It was about what MOM Z14 was showing us, a galaxy that shouldn't exist. When astronomers examined MOM Z14 more closely, they found multiple things that didn't make sense according to our models. First, its brightness. MOM-Z14 is exceptionally luminous for its age. It's about 100 times brighter than theoretical models predicted galaxies should be at this point in cosmic history. Before Webb launched, simulations suggested there might be a few bright galaxies in the very early universe, but not many. Webb has now found that bright early galaxies are common, not rare. They're everywhere we look in the early universe. This is a fundamental mismatch between theory and observation. Second, its size and compactness. MOM-Z14 spans about 240 light-years across. That might sound large, but for a galaxy, it's tiny. It's about 400 times smaller than the Milky Way. Yet within that small volume, it contains about 100 million times the mass of our Sun. That's roughly the same mass as the small Magellanic Cloud, a dwarf galaxy that orbits the Milky Way today. So MOM-Z14 has the mass of a substantial dwarf galaxy, but it's compressed into a space that's remarkably compact. This suggests it was in the middle of intense star formation, building itself rapidly through processes we don't fully understand. Third, its chemical composition. This is where things get really troubling. When astronomers analyzed the spectrum of light from MOM-Z14, they found something that shouldn't be there. Nitrogen. Lots of it. Now, you might wonder why nitrogen is such a problem. Here's why. When the universe began, it contained only the lightest elements, hydrogen and helium, with trace amounts of lithium. That's it. Everything else, every element heavier than helium, was created inside stars. Stars are cosmic furnaces, where nuclear fusion converts lighter elements into heavier ones. When massive stars die in supernova explosions, they scatter these newly created elements into space, enriching the gas that will form the next generation of stars. This process takes time. A star needs to form, live its life, and die before the elements it created can be incorporated into new stars. For elements like nitrogen, which are created through specific fusion processes in stellar cores, you need multiple generations of stars. You need enough time for the universe to build up these elements gradually, cycle by cycle, generation by generation. But MOM-Z14 existed when the universe was only 280 million years old. That's barely enough time for even one generation of stars to live and die. The massive stars that would have formed first in the universe might have lifetimes of just a few million years. So mathematically, you could fit several generations into 280 million years. But the amount of nitrogen detected in MOM-Z14 suggests more enrichment than current models say should be possible in that time frame. The nitrogen-to-carbon ratio observed in this galaxy is similar to what we see in globular clusters in the Milky Way. These are some of the oldest star clusters in our galaxy, containing stars that formed billions of years ago. But they had billions of years to accumulate that chemical signature. MOM-Z14 had a fraction of that time. One theory astronomers are considering is that the extreme density of the early universe might have allowed the formation of supermassive stars that don't exist today. Stars hundreds or even thousands of times more massive than our Sun, capable of fusing elements much more rapidly than normal stars. These hypothetical supermassive stars could have lived fast, died young, and enriched their surroundings with heavy elements in just a few million years. But we've never seen such stars, and the physics of whether they could even form is still uncertain. Fourth, the lack of neutral hydrogen. In the early universe, space was filled with neutral hydrogen gas. This gas acted like a thick fog, absorbing ultraviolet light and making the universe opaque to certain wavelengths. The first stars and galaxies began producing intense ultraviolet radiation that gradually ionized this hydrogen, breaking it apart and clearing the fog in a process astronomers call reionization. This process was supposed to happen gradually over hundreds of millions of years, as more and more stars formed and contributed their radiation to clearing the cosmic fog. But MOM Z14 shows signs that the space around it has already been cleared of neutral hydrogen. The galaxy's light shows characteristics indicating that it's sitting in a bubble of ionized space, a region where the fog has already been lifted. This means reionization began earlier than models predicted, much earlier. The galaxy seems to be producing enormous amounts of energetic photons, ultraviolet light, with enough energy to break apart hydrogen atoms. These photons have traveled through what appears to be a relatively dust-free environment, ionizing the hydrogen in the immediate vicinity of the galaxy. This is exactly what astronomers expected to happen, eventually, in the early universe. But not this early. Not when the universe was only 280 million years old. The galaxy appears to be doing this on its own, carving out its own clear bubble in the cosmic fog, suggesting that individual galaxies might have been more powerful than we thought in driving reionization. MOM Z14 also appears to be going through an intense burst of star formation. The light from the galaxy suggests it's forming new stars at a rapid rate, possibly creating hundreds or thousands of solar masses worth of new stars every year. For comparison, the Milky Way today forms only about 1 to 2 solar masses worth of new stars per year. MOM Z14, despite being much smaller, was forming stars hundreds of times faster. This burst of star formation would explain both the galaxy's brightness and its chemical enrichment. Rapid star formation means lots of massive stars, and massive stars both shine brightly and enrich their environment quickly when they die. But it raises another question. Where did all the gas come from to fuel this intense star formation? Galaxies need large reservoirs of cold gas to form stars, and in the early universe, that gas should have been more diffuse, more spread out. How did MOM Z14 gather enough gas, quickly enough, to support such intense star formation so early in cosmic history? The current leading theory is that the early universe was more clumpy than we thought. Maybe dark matter, which makes up about 85% of all matter in the universe, formed denser clumps earlier than our models predicted. These dense dark matter clumps would have strong gravitational fields, capable of pulling in normal matter more rapidly. If dark matter was clumpier earlier on, it could explain how galaxies like MOM Z14 assembled so quickly. But this is just a hypothesis. We don't fully understand dark matter yet, so adding it as an explanation for early galaxy formation is somewhat unsatisfying. We're using one mystery to explain another. Another possibility is that star formation in the early universe was simply more efficient than it is today. Today, when gas collapses to form stars, most of it doesn't actually become stars. Much of it gets blown away by radiation from the stars that do form, or gets heated to temperatures that prevent further collapse. Star formation today is inefficient. Maybe only 1 to 10% of available gas actually becomes stars. But in the early universe, conditions were different. The gas was denser, the environment was more turbulent, and feedback processes that prevent star formation today might not have been as strong yet. Maybe early galaxies converted gas into stars much more efficiently, forming more stars from less gas. This would explain why galaxies like MOM Z14 could build up so quickly. But again, this is speculation. We don't have direct evidence for more efficient star formation in the early universe. We're inferring it from the fact that galaxies like MOM Z14 exist when they shouldn't. Then there's the question of what MOM Z14 looked like structurally. The galaxy appears remarkably compact, with most of its light coming from a central region. This suggests it might not have had the complex spiral or elliptical structure we see in galaxies today. Instead, it was probably more like a dense blob of stars, all forming rapidly in a relatively small volume of space. These compact galaxies were probably the building blocks that would later merge to form larger galaxies like the Milky Way. But seeing them in action, watching them form in real time, well, billions of years ago in real time, challenges our understanding of how that process worked. One of the most troubling aspects of MOM Z14 and galaxies like it is what astronomers call the growing chasm between theory and observation. This phrase comes directly from the scientific papers describing these discoveries. A chasm between what we thought the universe would look like at this early time and what Webb is actually showing us. Our models of galaxy formation are based on well-established physics. We understand gravity. We understand how gas cools and collapses. We understand nuclear fusion. We understand the life cycles of stars. These aren't guesses. They're processes we've studied in detail, both theoretically and through observations of the modern universe. Yet, when we take those same processes and run them backward in time, simulating what the early universe should have looked like, we get predictions that don't match reality. The simulations produce far fewer bright galaxies than Webb is seeing. The simulations predict that galaxies should be smaller and less chemically enriched at early times than what Webb is measuring. The simulations suggest reionization should happen later and more gradually than the evidence suggests. This doesn't mean the physics is wrong, at least not entirely. It means we're missing something important in our models. Maybe it's the behavior of dark matter in the early universe. Maybe it's the efficiency of star formation. Maybe it's the role of supermassive black holes, which might have formed earlier than we thought and influenced galaxy evolution in ways we haven't accounted for. Maybe it's something we haven't even considered yet. This is genuinely troubling for astronomers, because the whole point of science is to build models that predict what we'll observe. When observations consistently contradict predictions, it means the models need to change. But changing models of the early universe isn't simple. These models are interconnected with so many other aspects of cosmology. If you change how galaxies form, you might affect predictions about the cosmic microwave background. If you change the timeline of reionization, you might affect predictions about the distribution of elements in the universe. Everything is connected, so you can't just tweak one part of the model without checking whether those changes break something else. This is why MOM Z14 is more than just another distant galaxy. It's a challenge to our entire framework for understanding cosmic history. Now, let's talk about what MOM Z14 actually is in physical terms. This galaxy currently exists 33.8 billion light-years away from Earth. You might wonder how it can be farther than 13.53 billion light-years if its light has only been traveling for 13.53 billion years. The answer is cosmic expansion. While the light from MOM Z14 was traveling toward us, the universe was expanding, stretching the space between us and the galaxy. So even though the light has been traveling for 13.53 billion years, the galaxy itself has been carried away by expansion to a much greater distance. If we could somehow teleport to where MOM Z14 is right now, we'd be 33.8 billion light-years from Earth. But we can't see the galaxy as it is right now. We can only see it as it was 13.53 billion years ago when the light we're receiving left the galaxy. What does MOM Z14 look like today? In its present state, we don't know. It might have merged with other galaxies to become part of a much larger structure. It might be unrecognizable compared to what we see in Webb's images. It's even possible, though unlikely, that it's been destroyed or disrupted somehow. We can never know what's happening there right now because the light showing us the current state won't reach us for another 33.8 billion years. And by that time, the universe will have expanded so much that the light might be too faint to detect, even with telescopes far more advanced than Webb. This is one of the strange implications of cosmic distances. The farther away something is, the more we're seeing its past, not its present. And for the most distant objects, the present is forever hidden from us. The light from MOM Z14 has been traveling through space for so long that the photons arriving at Webb's mirrors right now began their journey when the universe was radically different from how it is today. When that light left MOM Z14, there were no stars like our Sun. There were no planets like Earth. There was no Milky Way galaxy as we know it. The universe was young, hot, dense, and filled with the first generation of galaxies struggling to form in the cosmic dark. Those photons traveled through expanding space for 13.53 billion years, passing through regions where other galaxies were forming, regions where dark matter was coalescing, regions where the cosmic web of structure was just beginning to take shape. They traveled across distances so vast that human minds can barely comprehend them. And finally, on May 16th, 2025, a tiny fraction of those photons arrived at a telescope built by beings on a small planet orbiting an ordinary star in an ordinary galaxy. And we captured that light, analyzed it, and learned something profound about where we came from. There's something deeply moving about that. These photons traveled for almost the entire history of the universe to reach us. They carry information about conditions so alien, so unlike anything in the modern cosmos, that we struggle to model or understand them. But we can read that information. We can decode the message carried by those ancient photons. We can learn what the universe was like when it was just 2% of its current age. That's extraordinary. Let's put MOM Z14's distance in another perspective. Light travels at 186,000 miles per second. In 1 year, light travels about 5.88 trillion miles. The light from MOM Z14 has been traveling for 13.53 billion years. That means the light has covered a distance, accounting for cosmic expansion, of about 13.53 billion light-years in travel time. But the actual current distance, as mentioned, is 33.8 billion light-years due to expansion. To put it mildly, this is incomprehensibly far. If you could somehow travel at the speed of light, which is physically impossible for anything with mass, it would still take you 13.53 billion years to reach where MOM Z14 was when it emitted the light we're seeing now. And if you wanted to reach where it is currently, you'd have an even more impossible journey ahead of you, because the universe is still expanding, carrying the galaxy away from us faster than you could travel, even at light speed. In a real sense, MOM Z14 and galaxies like it are already beyond our reach. Even if we develop technology to travel at near light speed, which is far beyond anything we can imagine building, we could never reach these distant galaxies because the expansion of the universe is carrying them away faster than we could chase them. This is a sobering reality of cosmology. Most of the universe is forever beyond our physical reach, separated from us not just by distance, but by the expansion of space itself. We can observe these distant regions, we can study them, we can learn from them, but we can never visit them. Now, let's discuss what the discovery of MOM-Z14 means for our understanding of cosmic evolution. The universe has a timeline, a sequence of events that led from the hot, dense state immediately after the Big Bang to the complex cosmos we inhabit today. This timeline was thought to be fairly well understood. The Big Bang happened 13.8 billion years ago. For the first 380,000 years, the universe was too hot for atoms to form. Matter and radiation were mixed together in a dense plasma. Then the universe cooled enough for electrons and protons to combine into hydrogen and helium atoms. This is called recombination. After recombination, the universe entered what astronomers call the cosmic dark ages. There were no stars yet, just hydrogen and helium gas slowly collapsing under gravity. This period lasted for hundreds of millions of years. Then, gradually, the first stars formed. These were probably massive, hot stars that burned bright and died young, creating the first heavy elements and beginning the process of enriching the universe with the chemical ingredients needed for planets and life. As more stars formed and died, small galaxies began to take shape. These early galaxies merged with each other over time, building larger structures. Eventually, after billions of years, you get galaxies like the Milky Way. Reionization happened somewhere in this timeline, as the ultraviolet light from early stars gradually cleared the neutral hydrogen fog that filled space. This whole process was thought to take time, measured in hundreds of millions to billions of years. But MOM-Z14 and other Webb discoveries are compressing that timeline. They're showing us that bright, massive, chemically enriched galaxies existed much earlier than the models predicted. The cosmic dark ages might have been shorter than we thought. The first stars might have formed earlier. Galaxies might have assembled more quickly. Reionization might have begun sooner and happened faster. All of these changes to the timeline have cascading effects on our understanding of cosmic history. If galaxies formed earlier, then the structures we see today, the clusters and superclusters of galaxies, might have had more time to develop than we thought. If reionization happened earlier, it affects our models of how light from the early universe propagated through space. If star formation was more efficient early on, it changes our understanding of how elements were distributed throughout the universe. Every piece of the cosmic timeline is connected to every other piece, so changing one part means re-examining everything else. This is the exciting and frustrating part of frontier science. Every new discovery raises as many questions as it answers. Webb was built to answer questions about the early universe, and it's doing that. But the answers it's providing are showing us that our questions were based on incomplete understanding. We weren't asking the right questions because we didn't know what we didn't know. Now we're learning what we don't know, and it's humbling. There's also the question of whether MOM-Z14 is unusual or typical. Is it a rare outlier, a galaxy that formed under extraordinary circumstances that we just happened to discover? Or is it representative of what most galaxies looked like at that time? The Mirage or Miracle survey found that MOM-Z14 is not alone. There are many bright galaxies at similar distances, all showing similar characteristics. This suggests that bright, compact, chemically enriched galaxies were common in the early universe, not rare. If they're common, that's a bigger problem for our models, because it means the models are systematically wrong, not just missing a few special cases. It means the processes that formed these early galaxies were operating in ways we haven't captured in our simulations. The good news, if you can call it that, is that Webb is providing the data needed to solve this puzzle. Every new observation of early galaxies, every spectrum, every measurement of chemical composition and star formation rate adds to the dataset that theorists can use to refine their models. Eventually, someone will figure out what's missing from the models. Maybe it'll be a breakthrough in understanding dark matter behavior. Maybe it'll be a realization about star formation efficiency. Maybe it'll be something completely unexpected. But the path to that breakthrough starts with observations like MOM Z14. Another instrument that will help solve this puzzle is the Nancy Grace Roman Space Telescope, scheduled to launch in May 2026. Roman will have a field of view about 100 times larger than Webb, allowing it to survey much larger areas of sky in less time. While Webb is excellent at studying individual objects in exquisite detail, Roman will be excellent at finding large numbers of objects and identifying patterns in their distribution and properties. Together, Webb and Roman will provide complementary views of the early universe. Webb will give us the deep, detailed studies of individual galaxies like MOM Z14. Roman will tell us how common such galaxies are, where they're located in the cosmic web, and how their properties vary across different regions of space. With data from both telescopes, astronomers will be able to build a more complete picture of the early universe and hopefully resolve the growing chasm between theory and observation. Let's take a moment to appreciate the technology that made the discovery of MOM Z14 possible. The James Webb Space Telescope is a marvel of engineering. Its primary mirror is 21.3 feet in diameter, composed of 18 hexagonal segments that had to unfold and align perfectly after launch. Each segment is coated with a microscopically thin layer of gold, which reflects infrared light efficiently. The telescope operates at extremely cold temperatures, about -390 degrees Fahrenheit, to prevent its own heat from interfering with the faint infrared signals it's trying to detect. It's stationed at a point in space called L2, about 1 million miles from Earth, where it can observe continuously without being blocked by Earth or heated by the sun. Webb's near-infrared spectrograph, the instrument that measured MOM's Z14 spectrum, is capable of analyzing light with incredible precision. It can detect individual emission lines from ionized atoms, measuring their exact wavelengths and strengths. This allows astronomers to determine not just how far away an object is, but what it's made of, how fast it's forming stars, whether it contains dust, and many other properties. The spectrograph achieves this by dispersing light into its component wavelengths, like a prism spreading sunlight into a rainbow. But Webb's spectrograph operates in the infrared, detecting wavelengths of light that are invisible to human eyes. This is crucial for studying the early universe because redshift pushes visible light into the infrared. Galaxies like MOM Z14 emitted visible and ultraviolet light, but after traveling for 13.53 billion years through expanding space, that light has been stretched into the infrared part of the spectrum. Webb can see that infrared light, while visible light telescopes like Hubble cannot. This is why Webb can see farther back in time than Hubble. It's not just that Webb is bigger, though it is. It's that Webb is optimized for infrared observations, which is exactly what you need to study the most distant objects in the universe. The discovery process for MOM Z14 also required sophisticated data analysis. The raw images from Webb contain thousands of galaxies, and identifying which ones are potentially from the early universe requires careful examination of how they appear in different filters. MOM Z14 is invisible in some of Webb's filters, but bright in others. This pattern, called a dropout, indicates that the galaxy's light has been redshifted so much that certain wavelengths aren't visible at all. Astronomers use these dropout patterns to identify candidate early galaxies, then follow up with spectroscopy to confirm their distances. The spectroscopic follow-up is crucial because photometry alone, just measuring brightness in different filters, can be ambiguous. Some nearby dusty galaxies can mimic the appearance of distant galaxies, which is why the Mirage, or Miracle survey, was necessary. By taking detailed spectra, astronomers can definitively measure redshift and rule out alternative explanations. In MOM Z14's case, the spectrum showed multiple emission lines that could be precisely identified and measured. These lines come from ionized atoms in the galaxy's hot gas, things like oxygen, neon, and nitrogen. By measuring how much these lines have been redshifted, astronomers calculated the galaxy's redshift value of 14.44 with high confidence. There's no ambiguity. MOM Z14 really is that distant and that ancient. The spectrum also revealed information about the galaxy's star formation rate and chemical composition, providing the additional details that make MOM Z14 such a puzzle. Now, let's talk about what MOM Z14 tells us about the possibility of life in the universe. This might seem like a strange connection, but bear with me. Life, as we know it, requires certain chemical elements: carbon, nitrogen, oxygen, phosphorus, sulfur, and others. These elements weren't present in the early universe. They had to be created in stars. So for life to emerge anywhere, you first need stars to form, live their lives, and die, scattering these essential elements into space. Then you need second or third generation stars that form from gas already enriched with these elements. Then you need planets to form around those stars. Then you need the right conditions on those planets for life to emerge. This whole sequence takes time. In our solar system, it took about 9 billion years from the Big Bang until Earth formed 4.5 billion years ago. Then, it took nearly 1 billion years more for life to arise on Earth. So from the Big Bang to the emergence of life on Earth was about 10 billion years. But MOM Z14 is showing us that chemical enrichment happened much faster than we thought. If nitrogen and other heavy elements were being produced abundantly when the universe was only 280 million years old, that potentially moves up the timeline for when planets and possibly life could have formed elsewhere in the universe. It doesn't mean life formed that early. The conditions in the early universe were probably too turbulent for stable planetary systems to exist. But it does mean that the chemical prerequisites for life were in place earlier than our old models suggested. This is relevant when we think about the Fermi paradox, the question of why we haven't detected signs of alien civilizations if the universe is so vast and so old. One proposed solution to the Fermi paradox is that life takes a very long time to evolve, and we're among the first intelligent civilizations to emerge. But if chemical enrichment happened faster than we thought, that potentially makes the universe habitable for life sooner, which would suggest there should have been more time for other civilizations to arise before us. This doesn't solve the paradox, but it does affect how we think about it. Of course, we still have no evidence of life anywhere beyond Earth. We're still searching, still listening, still looking for any sign that we're not alone. MOM Z14 doesn't change that fundamental uncertainty, but it does remind us that the universe has been capable of producing the building blocks of life for much longer than we realized. There's something profound about the fact that we can study a galaxy that existed when the universe was so young and learn that it was already enriched with elements essential for life. Those elements were created in stars that formed, lived, and died in the first few 100 million years of cosmic history. Some tiny fraction of those elements might be in your body right now, recycled through billions of years of cosmic evolution, incorporated into the sun when it formed, passed into planets, and eventually into living things. You're made of atoms that might have been created in galaxies like MOM Z14, scattered into space by supernovas in the early universe, then recycled countless times before becoming part of you. That connection across time and space is one of the most beautiful insights modern astronomy provides. Let's address something important. The discovery of MOM Z14 doesn't mean the Big Bang theory is wrong. You might have seen headlines or social media posts claiming that Webb's discoveries prove the Big Bang never happened. This is not true. The Big Bang theory is supported by an enormous body of evidence from multiple independent sources. The cosmic microwave background radiation, the abundance of light elements like hydrogen and helium, the expansion of the universe, the distribution of galaxies. All of these observations are explained by the Big Bang model. What MOM Z14 and other Webb discoveries challenge is not the Big Bang itself, but our models of what happened after the Big Bang. Specifically, our models of how quickly galaxies formed and how efficiently stars formed in the early universe. These are details within the larger Big Bang framework, not challenges to the framework itself. Science works by testing models against observations and refining the models when they don't match. That's exactly what's happening now. Astronomers are taking the data from Webb and using it to improve their models of early galaxy formation. This is how science progresses. It's not a crisis. It's an opportunity to learn and to develop better, more accurate models. The troubling part, the part that makes MOM Z14 so significant, is not that it contradicts the Big Bang, but that it contradicts specific predictions about the early universe that were based on decades of careful work. When predictions fail this dramatically, it means there's something important we didn't understand. And finding out what that something is will advance our knowledge significantly. This is genuinely exciting for astronomers, even if it's also frustrating and humbling. Every major breakthrough in understanding comes from observations that don't fit existing models. MOM Z14 might be one of those breakthrough observations. Now, let's think about the future. MOM Z14 currently holds the record as the most distant galaxy ever confirmed. But that record probably won't stand for long. Webb is continuing to observe the early universe, and the Roman Space Telescope will join the search soon. There are likely galaxies even more distant than MOM Z14 waiting to be discovered. How far back can we see? There's a theoretical limit, called the cosmic horizon. We can't see farther than the distance light has traveled since the Big Bang, accounting for expansion. The cosmic horizon is currently about 46.5 billion light-years away in any direction. Beyond that, light hasn't had time to reach us yet. The most distant objects we could possibly observe would be from about 200 million years after the Big Bang, when the very first stars began to form. Before that, there were no luminous objects to observe, just dark clouds of hydrogen and helium gas. Webb might be able to see galaxies from that era, or it might not. It depends on whether any galaxies formed that early, and whether they're bright enough to be detected. but we're getting close to the limits of what's possible with current technology. To push much farther back in time would require even more sensitive instruments, possibly a telescope even larger than Webb operating in space. There are already concepts being discussed for next-generation space telescopes, but they're decades away from being built. For now, Webb and soon, Roman represent the cutting edge of our ability to observe the early universe. Every discovery they make, like MOM Z14, is precious because it's showing us a part of cosmic history that's never been seen before. We're living through a golden age of cosmological discovery. Never before in human history have we been able to see so far, to peer so deeply into the universe's past, to test our theories against such direct observations of the early cosmos. Our ancestors could only wonder about the origins of the universe. We can actually observe them, at least in part. That's extraordinary. Before we go further, let's take a step back and really understand what redshift means and why it's so crucial to this story. When astronomers measure the distance to galaxies like MOM Z14, they're not using a ruler or measuring tape. They're using the properties of light itself. Light is a wave, and like all waves, it has a wavelength, the distance between successive peaks. Different wavelengths of light appear as different colors to our eyes. Red light has longer wavelengths, blue light has shorter wavelengths. When light travels through expanding space, the expansion stretches the wavelength. This is called redshift, because the light shifts toward longer, redder wavelengths. The amount of redshift tells us how much the universe has expanded since the light was emitted. A small redshift means the light hasn't traveled very far, and the universe hasn't expanded much since the light began its journey. A large redshift means the light has traveled across vast distances, and the universe has expanded significantly. MOM Z14 has a redshift of 14.44. This is an enormous value. It means the universe has expanded by a factor of about 15.44 since the light left the galaxy. When the light left MOM 14, the universe was about 15 times smaller than it is today. Everything was closer together, denser, hotter. The light that left MOM Z14 as ultraviolet radiation, with wavelengths of about 200 to 300 nanometers, has been stretched by cosmic expansion into infrared light with wavelengths of about 3 to 4 microns. That's why Webb, with its infrared sensors, is essential for detecting these distant galaxies. By the time their light reaches us, it's been redshifted, completely out of the visible spectrum. Now, here's something mind-bending about redshift. As you look at objects with higher and higher redshift, you're not just looking farther away. You're looking at a universe that's fundamentally different. At a redshift of 0, you're looking at the modern universe as it is today. At a redshift of 1, you're looking at the universe when it was about half its current age, about 6 billion years ago. At a redshift of 2, you're looking back about 10 billion years, when the universe was forming stars at a much higher rate than today. At a redshift of 6, you're looking at the universe when it was less than 1 billion years old, when the first galaxies were forming and reionization was underway. And at a redshift of 14.44, you're looking at an alien cosmos. A universe that's 2% of its current age. A universe where most of the familiar structures don't exist yet. A universe that's still finding its way, still forming the building blocks that will eventually become the galaxies we see around us today. This is why MOM Z14 is so valuable. It's not just a distant galaxy, it's a window into a completely different epoch of cosmic history. An epoch we can barely access because the light from that time is so faint and so redshifted that it requires the most powerful telescopes humanity has ever built just to detect it. Let's talk more about what the universe was like when MOM Z14's light began its journey, 280 million years after the Big Bang. The universe at that time was about 1/15 its current size. It was denser by a factor of about 3,375, because density scales with the cube of the size. It was hotter than it is today, though not drastically so, in the regions where galaxies were forming. The cosmic microwave background, the afterglow of the Big Bang, would have had a temperature of about 41 degrees Fahrenheit, instead of the -454 degrees it has today. Still cold, but warmer than interstellar space is now. The night sky would have looked completely different. There were fewer stars, but they were closer together. If you could somehow stand on a planet in MOM Z14 and look up, you'd see nearby galaxies much closer and brighter than distant galaxies appear to us today. The cosmic web of structure, the vast filaments and voids that define the large-scale structure of the universe today, was just beginning to form. Dark matter had already started clumping under its own gravity, creating the gravitational wells into which normal matter would fall. But the process was in its early stages. Most of the universe was still relatively smooth and uniform. The intergalactic medium, the gas between galaxies, was mostly neutral hydrogen. This gas absorbed ultraviolet light, making the universe opaque at certain wavelengths. It was like a fog, filling all of space, and the first galaxies were just beginning to clear that fog in their immediate vicinity. The density of matter was higher, which meant gravitational interactions were stronger. Galaxies were probably colliding and merging more frequently than they do today. The universe was a more violent, chaotic place. Star formation rates across the universe were probably higher than today's average. More gas was available, compressed into smaller volumes, making it easier for gravity to pull it together into star-forming regions. The universe was younger, but in some ways more active. This is the environment in which MOM Z14 formed, a universe barely out of its infancy, still finding its equilibrium, still evolving rapidly. Now, let's consider the observational challenges of studying objects like MOM Z14. These galaxies are among the faintest objects ever detected. The light that reaches Webb from MOM Z14 is incredibly dim. After traveling for 13.53 billion years, spreading out across an ever-expanding sphere, the light has been diluted to almost nothing. The total amount of energy Webb collects from MOM Z14 during an observation is less than the energy required to lift a single grain of sand 1 millimeter. It's barely there, just a whisper of light against the cosmic background. Detecting such faint signals requires extraordinary sensitivity. Webb's mirrors need to be precisely shaped and aligned. Its sensors need to be cooled to near absolute zero to minimize noise from thermal radiation. Its electronics need to be carefully designed to amplify weak signals without introducing distortion. And even with all that technology, astronomers need to point Webb at the same patch of sky for hours or even days to collect enough photons to create a usable image. The observations that discovered and confirmed MOM Z14 required multiple visits to the same region of sky. First, broad surveys using Webb's camera to identify candidate galaxies. Then targeted spectroscopic observations to measure their redshifts precisely. Each observation requires careful planning. Webb's time is precious and highly competitive. Astronomers from around the world submit proposals for observations, and only a fraction are accepted. The teams studying early galaxies like MOM Z14 had to justify why their observations were important enough to deserve Webb's limited time. They had to design observation strategies that would maximize the scientific return while minimizing the time required. The data analysis is equally challenging. Webb's instruments produce enormous amounts of data, terabytes of information that need to be processed, calibrated, and analyzed. Extracting the faint signal of a galaxy like MOM Z14 from the background noise and from the light of other objects in the same field of view requires sophisticated algorithms and careful attention to detail. A single error in data processing could lead to incorrect conclusions. Astronomers need to check and recheck their work, verify their results through independent analysis, and test whether alternative explanations could account for what they're seeing. This is why the confirmation of MOM Z14 took months after it was first detected. The team needed to be absolutely certain that what they were seeing was real, that the redshift measurement was accurate, that they weren't being fooled by some artifact or unusual phenomenon. Science at this frontier requires extreme care and patience. The stakes are high because the conclusions affect our fundamental understanding of the universe. Let's also consider what MOM Z14 tells us about the distribution of matter in the early universe. Galaxies don't form randomly. They form in regions where matter is slightly denser than average. These density fluctuations, which we can see imprinted in the cosmic microwave background, are the seeds that grew into all the structure we see today. Dark matter, which doesn't interact with light, began clumping under gravity first. Its clumps created gravitational wells that attracted normal matter, gas that could cool, collapse, and form stars. The fact that MOM Z14 exists, when it does, tells us that density fluctuations in that region of space must have been significant. The dark matter had to clump early and densely enough to pull in enough gas to form a galaxy within the first few 100 million years. This isn't impossible, but it's on the edge of what our models predict should happen. Some regions of space, by random chance, would have higher than average density. Those regions would form galaxies earlier. MOM Z14 is probably one of those early forming regions, a place where conditions were just right for rapid galaxy assembly. But the fact that Webb is finding many such galaxies, not just one or two, suggests that these favorable conditions were more common than expected. Either the initial density fluctuations were larger than models predict, or dark matter clumped more efficiently, or normal matter fell into those clumps faster than we thought. Any of these possibilities would require revising our understanding of the early universe. Another factor is feedback. When stars form, they don't just sit there passively shining. They inject energy into their surroundings through radiation, stellar winds, and eventually supernova explosions. This energy heats the surrounding gas, sometimes blowing it out of the galaxy entirely. In modern galaxies, this feedback is a major factor limiting star formation. It prevents all the available gas from turning into stars, maintaining a balance between star formation and gas heating. But in the early universe, feedback might have worked differently. With denser gas and different chemical compositions, the balance between star formation and feedback could have favored more rapid star formation. Or perhaps feedback was weaker in the early universe, because the first stars formed in deep gravitational wells, where the gas was bound too tightly to be easily blown away. These are questions that MOM Z14 and other early galaxies can help answer. By studying how much gas they contain, how rapidly they're forming stars, and how their stellar populations evolve over time, astronomers can learn about the balance between star formation and feedback in the early universe. Let's also consider the role of supermassive black holes. Many modern galaxies have supermassive black holes at their centers, including our own Milky Way. These black holes contain millions or billions of times the mass of the Sun, and they profoundly influence their host galaxies. When gas falls into a supermassive black hole, it forms an accretion disk that heats up to millions of degrees and emits intense radiation. This radiation can blow away gas from the galaxy, shutting down star formation. It can also trigger star formation in some regions by compressing gas. The relationship between supermassive black holes and their host galaxies is complex and still not fully understood. One major question is when supermassive black holes formed. Did they form early in the universe's history, perhaps from the collapse of massive gas clouds or from the remnants of the first generation of stars? Or did they grow gradually over time, starting as smaller black holes and accumulating mass through mergers and accretion? Webb has found evidence that supermassive black holes existed earlier than expected, in some cases within the first few 100 million years after the Big Bang. This is another surprise, another challenge to models that predicted black holes should take longer to grow to supermassive sizes. MOM-Z14's spectrum doesn't show clear signs of an active supermassive black hole at its center. The light appears to come primarily from stars, not from an accretion disk. But that doesn't mean there isn't a black hole there. It might not be actively accreting material at the moment we're observing it. Or it might be there, but obscured by dust. Or it might be relatively small, not yet grown to supermassive sizes. Understanding the role of black holes in early galaxies, like MOM-Z14, is crucial for understanding how galaxies and black holes co-evolved. There's evidence that the mass of a galaxy's central black hole is related to the mass of the galaxy's bulge, suggesting a deep connection between black hole growth and galaxy formation. But how that connection was established, especially in the early universe, remains an open question. Let's also talk about what happens to galaxies like MOM-Z14 over cosmic time. We're seeing MOM-Z14 as it was 280 million years after the Big Bang. But the galaxy didn't stop there. It continued to evolve over the next 13.5 billion years. It probably merged with other galaxies, combining its stars and gas with theirs to form larger structures. Each merger would have triggered new bursts of star formation as gas clouds collided and compressed. The galaxy would have changed shape, perhaps transforming from the compact blob we see in Webb's images to a more extended spiral or elliptical galaxy. Its chemical composition would have become more enriched as successive generations of stars lived and died, creating heavier and heavier elements. By now, 13.5 billion years later, MOM-Z14 might be part of a large galaxy cluster, having merged with dozens or hundreds of other galaxies. Or it might still be recognizable as a distinct galaxy, just much larger and more evolved than when we see it. We can't know for certain, because we can only see its past, not its present. But we can compare MOM-Z14 to nearby galaxies to guess at its likely evolutionary path. Galaxies similar in mass and size to MOM-Z14 in the local universe tend to be satellite galaxies orbiting larger structures. So it's possible that MOM-Z14 eventually became part of a galaxy group or cluster, orbiting a larger galaxy, much like the small Magellanic Cloud orbits the Milky Way. Or perhaps it merged completely with a larger galaxy, its stars now indistinguishable from those of its merger partner. This is the fate of most small galaxies in the universe. They don't remain isolated forever. Gravity eventually brings them into contact with other galaxies, and mergers are the result. Over cosmic time, small galaxies are consumed by larger ones, building up the massive galaxies we see today. The Milky Way itself is the result of countless mergers over billions of years, and it's still in the process of consuming smaller satellite galaxies. MOM Z14 was probably one of the building blocks that eventually became part of some larger structure. A small piece in the vast puzzle of cosmic evolution. Now let's discuss the broader implications of discoveries like MOM Z14 for cosmology as a whole. Cosmology is the study of the universe at the largest scales, its origin, evolution, and ultimate fate. It's built on a foundation of observations, from the cosmic microwave background to the distribution of galaxies, to the behavior of distant supernovas. Each observation contributes to our understanding of fundamental cosmological parameters, like the age of the universe, the rate of expansion, the density of different forms of matter and energy, and the initial conditions that led to structure formation. Discoveries like MOM Z14 test our cosmological models in new ways. They push observations to earlier times, closer to the Big Bang, where the universe was in a very different state. If our models correctly describe the physics of the early universe, they should accurately predict what we'll see when we look at objects from that era. But as we've discussed, the predictions aren't matching observations perfectly. This suggests that something in our models needs adjustment. It might be a small adjustment, a tweak to parameters describing star formation efficiency or dark matter behavior. Or it might be something more fundamental, a missing piece of physics that becomes important in the extreme conditions of the early universe. Either way, reconciling observations with theory will advance cosmology. It will give us a more accurate, more complete picture of how the universe works. One possible resolution to the growing chasm between theory and observation involves re-examining the initial conditions of the universe. The tiny density fluctuations that eventually grew into galaxies are thought to have originated from quantum fluctuations in the very early universe, blown up to cosmic scales during a brief period of exponential expansion called inflation. The properties of these fluctuations, their amplitude and distribution, are constrained by observations of the cosmic microwave background, but there's some wiggle room in the models. If the initial fluctuations were slightly larger or distributed differently than the simplest models predict, it could lead to earlier and more rapid structure formation. This wouldn't overturn our understanding of inflation or the Big Bang. It would just refine the details. Another possibility involves the nature of dark matter itself. Dark matter is mysterious. We know it exists because of its gravitational effects, but we don't know what it's made of. Most models assume dark matter is cold, meaning it moves slowly compared to the speed of light. Cold dark matter clumps efficiently under gravity, forming the structures we see. But what if dark matter has properties we haven't accounted for? What if it interacts with itself in ways that affect how it clumps? What if there are multiple types of dark matter with different properties? These alternatives, while speculative, could potentially explain why structure formed earlier and more efficiently than standard cold dark matter models predict. Testing these ideas requires more observations, more detailed simulations, and more theoretical work. MOM Z14 and other early galaxies provide crucial data points for these efforts. Let's also consider what MOM Z14 tells us about the universe's overall timeline and evolution. The universe has a history, a sequence of major transitions that shaped its development. Understanding when these transitions occurred and how long they took is fundamental to cosmology. The Big Bang happened 13.8 billion years ago. Recombination, when atoms first formed, happened about 380,000 years after the Big Bang. The cosmic dark ages lasted from recombination until the first stars formed, probably between 100 and 200 million years after the Big Bang. The epoch of reionization, when ultraviolet light from stars cleared the neutral hydrogen fog, is thought to have lasted from about 200 million years to about 1 billion years after the Big Bang. MOM Z14, existing at 280 million years, places it right in the middle of reionization. Its apparent role in clearing its surrounding region of neutral hydrogen suggests that reionization was already underway at that time. This helps constrain the timeline, showing that reionization must have begun early, within the first few 100 million years. By studying many galaxies across this era, astronomers can map out how reionization proceeded, which regions cleared first, how long the process took, and what types of galaxies contributed most to clearing the fog. This is important because reionization was one of the last major phase transitions in cosmic history. After reionization, the universe became transparent to most wavelengths of light, allowing us to see deep into space. Understanding when and how this transparency was achieved is crucial for interpreting all the observations we make of the distant universe. Let's also address another question you might be wondering about. If galaxies like MOM Z14 are so surprising and challenging to our models, does that mean something is fundamentally wrong with modern cosmology? The short answer is no. The standard model of cosmology, often called lambda CDM, after its key components, dark energy and cold dark matter, is extraordinarily successful. It explains an enormous range of observations with just a handful of parameters. It correctly predicts the cosmic microwave background in exquisite detail. It explains the abundance of light elements, like hydrogen and helium. It explains the large-scale distribution of galaxies. It explains the accelerating expansion of the universe. These successes are not accidents. They're the result of decades of careful theoretical development and observational testing. MOM Z14 doesn't overturn any of this. What it challenges is our understanding of the details of structure formation, specifically how efficiently gas collapsed into galaxies and how rapidly stars formed in those early galaxies. These are complex processes involving gas dynamics, star formation, physics, feedback mechanisms, and chemical enrichment. They're not as well understood as the overall expansion of the universe or the behavior of dark matter at large scales. So when observations don't match predictions in this area, it's not a crisis for cosmology. It's an opportunity to refine our understanding of a specific process. Think of it like this. You can understand the overall structure of a building, its foundation and framework, without knowing every detail of the interior design. Lambda CDM is like the foundation and framework, solid and well-tested. The details of early galaxy formation are like the interior design, still being worked out, still requiring more data and better models. MOM Z14 is helping us work out those details. It's not undermining the foundation, it's revealing complexities in the interior that we hadn't fully appreciated. This is normal in science. Models are always being refined as new data becomes available. What matters is whether the overall framework holds up, and in cosmology, it does. Let's also consider the human story behind the discovery of MOM Z14. Science is often portrayed as a collection of facts and discoveries, but behind every discovery are people. Teams of astronomers, engineers, technicians, all working together toward a common goal. The James Webb Space Telescope represents the work of thousands of people over more than 2 decades. Engineers who designed and built its intricate mirrors and instruments. Scientists who proposed the mission and fought for its funding. Technicians who assembled and tested every component. Mission controllers who guided it through the nerve-wracking deployment process after launch. All of them contributed to making observations like MOM-Z14 possible. The discovery itself came from a specific team led by Rohan Naidu at MIT's Kavli Institute. This team includes astronomers from institutions around the world, a truly international collaboration. They designed the Mirage, or Miracle Survey, wrote the proposal to use Webb's observing time, analyzed the data when it came back, and wrote the scientific papers describing their findings. This process involves long hours, meticulous attention to detail, and intellectual creativity. It requires expertise in astrophysics, observational astronomy, data analysis, and scientific writing. It also requires patience. From the initial proposal to the publication of results can take years, and the work doesn't end with publication. The team continues analyzing the data, refining their models, presenting their results at conferences, and engaging with the broader scientific community. Science is collaborative and cumulative. Each discovery builds on previous work, and each team's results are checked and tested by others. The discovery of MOM-Z14 will inspire other teams to look for similar objects, to test the findings through independent observations, to incorporate the results into their own models and theories. This is how science progresses, through a collective effort spanning decades and involving thousands of contributors. And all of it driven by a simple human impulse, the desire to understand, to know where we came from, how the universe works, what else is out there. That impulse has driven exploration and discovery throughout human history, from ancient stargazers to modern cosmologists. MOM-Z14 is the latest chapter in that ongoing story. Let's also talk about what MOM-Z14 means for the search for cosmic dawn, the era when the first stars formed. Cosmic dawn is one of the last unexplored frontiers in observational cosmology. We have excellent observations of the cosmic microwave background, which shows us the universe as it was 380,000 years after the Big Bang. We have excellent observations of galaxies in the relatively recent universe within the last 10 billion years or so. But the period in between, especially the first few 100 million years after the Big Bang, has been largely hidden from us until recently. The first stars, called population 3 stars, were probably very different from stars today. They formed from gas that contained only hydrogen and helium, no heavier elements. This pure composition allowed them to grow more massive than modern stars, perhaps hundreds of solar masses. They would have burned incredibly hot and bright, and they would have lived fast and died young, exploding as supernovas after just a few million years. These first stars are crucial because they created the first heavy elements, seeding the universe with the ingredients needed for subsequent generations of stars and eventually for planets and life. But we've never seen one. They're too distant and too faint. Even for Webb, what we can see are the first galaxies, collections of early stars like those in MOM-Z14. These galaxies represent the aftermath of cosmic dawn, the structures that formed once the first stars had already created some heavy elements and begun enriching their surroundings. By studying these early galaxies, astronomers can infer what the first stars must have been like. If early galaxies are enriched with nitrogen and other elements, as MOM Z14 is, it tells us that supermassive population 3 stars must have formed, lived, and died before the galaxy we're observing came into being. The timeline matters. If galaxies like MOM Z14 existed 280 million years after the Big Bang, and they're already chemically enriched, then cosmic dawn must have happened even earlier. Maybe the first stars formed just 100 or 150 million years after the Big Bang. Webb might eventually be able to push back that far, detecting light from the very edge of cosmic dawn. But it will require extremely deep observations, longer exposure times, and careful data analysis. Every observation pushes the frontier back a little farther, revealing more about that crucial era when the universe transitioned from darkness to light. MOM Z14 is a signpost on that frontier, showing us that the universe was already active and complex by 280 million years. But there's still farther to go, still earlier epochs to explore. Let's also discuss what MOM Z14 and other early galaxies tell us about the cosmic web, the large-scale structure of the universe. Today, if you map out the locations of galaxies across the universe, you see a pattern. Galaxies are not distributed randomly. They're arranged in filaments, sheets, and clusters, with vast voids in between. This structure is called the cosmic web. It formed through gravitational collapse of the initial density fluctuations in the early universe. Regions that were slightly denser than average attracted more matter, becoming even denser over time. Regions that were slightly less dense lost matter to their denser neighbors, becoming voids. Over billions of years, this process created the web-like structure we see today. Dark matter, being more abundant and only interacting through gravity, formed the scaffolding of the cosmic web first. Normal matter followed, falling into the gravitational wells created by dark matter and forming galaxies where the dark matter was densest. MOM Z14 exists within this emerging cosmic web. It formed in a region where dark matter had already begun to clump, creating a gravitational well deep enough to attract and hold gas. That gas cooled, collapsed, and formed stars, creating the galaxy we see. But the cosmic web at that time was much less developed than it is today. The filaments were shorter, the voids less empty, the whole structure more compact. By studying where early galaxies like MOM Z14 are located and how they're distributed, astronomers can map out the cosmic web as it existed in the early universe. This provides crucial tests of models of structure formation, showing whether the observed distribution of early galaxies matches predictions. So far, there are hints that early galaxies might be more clustered than expected, more concentrated in dense regions. This could indicate that structure formation happened more efficiently in those dense regions. Or it could be an observational bias. We're more likely to detect galaxies in regions where there are many of them close together. More observations are needed to clarify this question. But it's clear that MOM Z14 and its neighbors are part of a cosmic structure that was already taking shape just a few 100 million years after the Big Bang. Let's also consider what MOM Z14 tells us about the universe's ultimate fate. The universe is expanding, and that expansion is accelerating, driven by something called dark energy that we don't understand. As the universe continues to expand, galaxies will move farther and farther apart. Eventually, billions of years in the future, the expansion will have carried distant galaxies so far away that their light can no longer reach us. the observable universe will shrink, not because the universe itself is shrinking, but because fewer and fewer distant regions will be within our cosmic horizon. In the very far future, perhaps hundreds of billions of years from now, the night sky will look different from how it looks today. Most galaxies will have been carried beyond the cosmic horizon by expansion. Only the galaxies in our local group, bound together by gravity, will remain visible. Astronomers in that distant future, if any exist, will look up and see a much emptier universe than we do. They won't be able to see the cosmic microwave background because it will have been redshifted into invisibility. They won't be able to see distant galaxies racing away from them. They might not even be able to deduce that the universe had a beginning, because the evidence for the Big Bang will have been carried beyond their reach by cosmic expansion. In a sense, we're living in a privileged time. We can still see the distant universe, still observe the cosmic microwave background, still study the evidence of the Big Bang. We can see galaxies like MOM-Z14 that show us what the universe looked like in its youth. Future astronomers, in the extremely distant future, might not have access to this information. They'll be limited to studying their local environment, unable to peer back to the beginning of time the way we can now. This makes our current observations all the more important. We're documenting a view of the universe that won't always be available. Every galaxy we catalogue, every spectrum we take, every measurement we make, is preserving knowledge about the cosmos that might otherwise be lost to future generations. MOM-Z14 might someday be beyond the cosmic horizon, forever unreachable and unobservable. But we've seen it, studied it, learned from it. That knowledge will persist, even if the galaxy itself becomes invisible. Now let's discuss the role of computer simulations in understanding galaxies like MOM-Z14. Modern cosmology relies heavily on computer simulations to model the universe's evolution. These simulations start with the initial conditions shortly after the Big Bang and evolve them forward in time using the laws of physics. They track how dark matter clumps under gravity, how gas flows and cools, how stars form and die, how black holes grow and emit energy. The most sophisticated simulations track billions of particles representing dark matter and gas, following their interactions over billions of years of simulated time. These simulations require some of the world's most powerful supercomputers, running for weeks or months to complete a single simulation run. When you run such a simulation and look at what emerges, you get a synthetic universe. You can measure properties of the simulated galaxies and compare them to observations of real galaxies. If the simulation matches reality, it suggests your model of galaxy formation is correct. If it doesn't match, something is missing from the model. Before Webb, simulations generally did a good job of matching observations of galaxies in the relatively recent universe. They predicted the right number of galaxies, the right range of masses and sizes, the right chemical compositions. But when those same simulations were used to predict what the very early universe should look like, they predicted far fewer bright galaxies than Webb is actually observing. This is the growing chasm between theory and observation. The simulations work well for recent cosmic history, but fail for the very early universe. This tells us that something about the early universe is different from our models. Maybe gas cooled and collapsed more efficiently than simulations predict. Maybe star formation was more efficient, converting a higher fraction of available gas into stars. Maybe feedback processes were weaker, allowing more stars to form before energy from the first stars heated and dispersed the gas. Maybe dark matter clumped faster or more strongly than the simulations assume. Or maybe some combination of all these factors created conditions that allowed rapid galaxy formation. Astronomers are now running new simulations, trying different assumptions and parameters to see if they can reproduce what Webb is seeing. Each new observation, like MOM-Z14, provides another data point to test the simulations against. Eventually, through this iterative process of simulation and observation, we'll arrive at models that correctly predict both the modern universe and the early universe. That's how science works. You propose a model, test it against observations, refine it when it fails, and repeat until you have a model that consistently matches reality. We're in the refinement phase right now, and MOM-Z14 is one of the observations driving that refinement. Let's also talk about what makes MOM-Z14 different from other early galaxies Webb has discovered. Webb has found hundreds of candidate early galaxies, objects that appear to be from the first few 100 million years after the Big Bang. MOM-Z14 is special because it's been spectroscopically confirmed. Spectroscopy, measuring the detailed spectrum of light from an object, is more time-consuming than just taking pictures, but it's also more definitive. It allows you to measure the exact redshift and rule out alternative explanations for what you're seeing. Many of the other early galaxy candidates identified by Webb are still waiting for spectroscopic confirmation. They might be as distant as they appear, or they might be nearby dusty galaxies masquerading as distant ones. We won't know until someone takes their spectra. MOM-Z14 has been confirmed, making it one of the most reliable data points we have about the early universe. It's also notable for being particularly compact and bright, even compared to other confirmed early galaxies. Its high nitrogen abundance is unusual, though other early galaxies also show unexpected chemical enrichment. What we're learning is that there's diversity among early galaxies, just as there is among modern galaxies. Some are more compact, some more extended. Some are forming stars rapidly, others more slowly. Some are chemically enriched, others more pristine. This diversity is actually valuable because it tells us that different environments and conditions in the early universe led to different outcomes. Not every region formed galaxies at the same rate or in the same way. By studying the full range of early galaxies, we can build a more complete picture of the processes at work. MOM-Z14 represents one end of that spectrum, a bright, compact, chemically enriched galaxy that formed remarkably early. Other galaxies represent different points in the parameter space. Together, they're helping us understand the full story of galaxy formation in the early universe. Let's also address a question you might be wondering about. Is there anything special about the direction in space where MOM-Z14 is located? The answer is no, and that's actually significant. MOM-Z14 was found in the cosmos field, a region of sky that astronomers have observed extensively with many different telescopes. This region was chosen not because there's anything special about that particular direction, but because deep observations already existed, making it a good target for follow-up studies. The fact that MOM-Z14 was found in a fairly typical region of sky suggests that galaxies like it are probably common throughout the universe. They're not confined to special regions or unusual environments. This is important because it means the processes that formed MOM-Z14 were operating throughout the early universe, not just in isolated pockets. If similar observations were made of other regions of sky, we'd probably find comparable galaxies. In fact, that's exactly what's happening. Webb is conducting surveys of multiple different fields, and early galaxies are being found in all of them. This reinforces the conclusion that the early universe was more active and populated than our models predicted. It's not a localized phenomenon, it's a universal one. Let's talk more specifically about the observations that confirmed MOM Z14's distance and properties. The team used Webb's near-spec instrument in what's called multi-object spectroscopy mode. This allows the instrument to observe multiple objects simultaneously by positioning small shutters to let through light from selected targets while blocking light from everything else. For MOM Z14, the team observed the galaxy for several hours, collecting enough photons to create a detailed spectrum. The spectrum showed several bright emission lines, peaks at specific wavelengths corresponding to light emitted by ionized atoms in the galaxy's gas. These lines come from elements like oxygen, neon, and nitrogen that have been ionized by the intense ultraviolet radiation from young stars. By measuring the exact wavelengths of these emission lines and comparing them to their laboratory wavelengths, astronomers could calculate the redshift. Each line was shifted toward longer wavelengths by the same factor, 14.44, confirming that this was indeed cosmological redshift caused by the expansion of the universe, not some other effect. The strength of the emission lines also provided information about the galaxy's properties. Strong emission lines indicate active star formation, with lots of hot, young stars producing ultraviolet radiation. The ratio of different emission lines tells you about the chemical composition and the physical conditions in the gas. From these measurements, the team could determine that MOM Z14 was forming stars rapidly and was enriched with elements like nitrogen to levels higher than expected for its age. The spectrum also showed a feature called the Lyman break, a sharp drop in brightness at wavelengths corresponding to ionized hydrogen absorption. This feature is characteristic of distant galaxies and provided additional confirmation of the high redshift. All of these pieces of evidence together, the redshift of the emission lines, their relative strengths, the Lyman break, paint a consistent picture of a galaxy that existed 280 million years after the Big Bang and was undergoing intense star formation. There's no ambiguity in this interpretation. The data is clear and compelling. Let's also consider the role that citizen scientists and public engagement play in discoveries like this. While the actual data analysis requires specialized expertise, the excitement and interest generated by discoveries like MOM Z14 help sustain public support for space telescopes and astronomical research. Webb was funded by taxpayers, primarily in the United States but also internationally. The decision to build such an expensive instrument was made by governments responding to public interest in space exploration and scientific discovery. Without that public support, Webb might never have been built. So, in a real sense, everyone who cares about space and astronomy contributes to making these discoveries possible. Your interest, your enthusiasm, your willingness to learn about these findings helps justify the investments needed to build the next generation of telescopes and instruments. There are also opportunities for more direct public participation. Some astronomical projects invite citizen scientists to help classify galaxies in images, identify interesting objects, or analyze data. While these projects typically focus on more recent galaxies that are easier for non-experts to work with, they help advance astronomy and give people hands-on experience with real scientific data. The knowledge you gain from learning about MOM Z14 might inspire you or someone you know to pursue astronomy or physics professionally. Many astronomers trace their interest back to a specific moment when they learned something about space that captured their imagination. Maybe MOM Z14 will be that moment for someone. Let's also discuss what MOM Z14 tells us about the cosmic timeline in human terms. The light we're seeing from this galaxy left it 13.53 billion years ago. That's hard to grasp. So let's put it in perspective. The Earth formed about 4.5 billion years ago. MOM Z14's light was already more than 9 billion years into its journey by the time Earth came into existence. When the light passed through the region where our solar system would eventually form, that region was just a diffuse cloud of gas and dust, part of the galactic disk, with no hint of what was to come. The light continued traveling as the solar system formed, as Earth differentiated into core, mantle, and crust, as the first oceans appeared, as the first life emerged about 3.8 billion years ago. It traveled as life evolved from single cells to complex multicellular organisms, as plants colonized the land, as dinosaurs ruled and went extinct, as mammals diversified and eventually gave rise to primates. It traveled as our human ancestors evolved in Africa, as they spread across the world, as they developed language, agriculture, civilization, writing, science. It traveled as ancient astronomers mapped the stars, as Copernicus and Galileo revealed that Earth orbits the Sun, as Newton described gravity, as Einstein developed relativity. It traveled as we built the first telescopes, sent the first spacecraft beyond Earth, landed humans on the Moon, launched Hubble, and finally launched Webb. And then, in 2025, that ancient light finally reached Webb's mirrors. After a journey lasting almost the entire history of the universe, those photons were captured, analyzed, and revealed their secrets. This is the extraordinary thing about astronomy. We're time travelers. We can't visit the past directly, but we can see it by looking at distant objects whose light has been traveling for billions of years. Every observation of a distant galaxy is an observation of the past. And with MOM Z14, we're seeing almost as far back as it's possible to see, to an era when the universe was barely beginning to take shape. Let's talk about what questions remain unanswered about MOM Z14 and what future observations might reveal. One key question is, what happened to this galaxy over the subsequent billions of years? Did it remain isolated, growing slowly through gas accretion and continued star formation? Or did it merge with other galaxies, becoming part of a larger structure? We can't observe MOM Z14's present state because it's too far away, but we might be able to track its probable evolutionary path by studying similar galaxies at different cosmic times. If we can find galaxies that look like what MOM Z14 might have evolved into at redshift 10, or redshift 5, or redshift 2, we can piece together a plausible history. This is like watching a movie by seeing single frames from different movies and trying to understand the plot. It's not perfect, but with enough observations, patterns emerge. Another question is whether MOM Z14 is truly representative of early galaxies or if it's an outlier. Is its high brightness, rapid star formation, and chemical enrichment typical of galaxies at that time, or was it unusually active? More observations of more early galaxies will help answer this. There's also the question of whether MOM Z14 contained planets. We have no way of detecting planets around stars in a galaxy this distant. The planets would be far too faint. But we can ask whether conditions in MOM Z14 would have allowed planet formation. With its rapid star formation and chemical enrichment, heavy elements were certainly present. But the environment might have been too turbulent, with frequent supernova explosions and intense radiation, potentially disrupting the protoplanetary disks where planets form. Or maybe planets did form, hardy worlds orbiting stars in the midst of this cosmic cauldron. If so, what might the view be like from such a planet? Looking up, You'd see a sky crowded with bright stars, all young and blue. You'd see nearby star-forming regions, glowing nebulae where new stars were being born. You'd see the remnants of recent supernovas, expanding shells of gas lit from within by the energy of the explosion. And beyond, you'd see other nearby galaxies, still close together, not yet separated by billions of light years of cosmic expansion. It would be a spectacular, violent, dynamic universe, nothing like the relatively calm cosmic environment we inhabit today. Whether any life existed to witness that spectacle, we'll probably never know. But it's fascinating to imagine. Let's also discuss the philosophical implications of MOM Z14. This galaxy existed when the universe was unimaginably young. The atoms that make up your body didn't exist yet, at least not in their current form. Some of them might have been hydrogen atoms in MOM Z14 or similar galaxies, waiting to be fused into heavier elements in stellar cores. Or they might have been part of the neutral hydrogen fog, filling intergalactic space, waiting to be ionized by the first starlight. Those atoms have been on a journey almost as long as the universe itself. Cycled through stars, blown into space by supernovas, incorporated into new stars, eventually finding their way into the gas cloud that formed our solar system, and finally into Earth and into you. You're made of recycled stardust, and some of that dust might trace its origins to galaxies like MOM Z14. There's also something profound about the fact that we can see MOM Z14 at all. The light from this galaxy has traveled for 13.53 billion years across expanding space, surviving the journey intact enough that we can capture it, analyze it, and learn from it. Think about how improbable that is. Those specific photons that happen to be aimed in just the right direction to eventually reach the tiny patch of space where Earth would form billions of years later. Those photons that survive the journey without being absorbed by dust or scattered by matter. Those photons that happen to arrive at precisely the moment in cosmic history when a species on a small planet had developed the technology to detect them. The odds against any particular photon making that complete journey are astronomical. And yet, enough photons made it that we can see the galaxy clearly, measure its properties, and learn its story. We're connected to MOM Z14 across 13.53 billion years and 33.8 billion light-years of space by these tiny messengers. Photons that have been traveling since before the sun existed. That connection is tenuous, fragile, improbable, but it's real. And it allows us to peer back into the universe's past and witness the birth of structures that would eventually lead to our own existence. Let's also consider MOM Z14 in the context of the broader search for our cosmic origins. Where did we come from? This is one of the most fundamental questions humans ask. On a personal level, you came from your parents, your grandparents, your ancestors stretching back through human history. On a biological level, humans evolved from earlier primates, who evolved from earlier mammals, who evolved from earlier vertebrates, all the way back to the first single-celled life on Earth. On a planetary level, Earth formed from the collapse of the solar nebula, a cloud of gas and dust left over from previous generations of stars. On a cosmic level, that gas and dust came from stars like those in MOM Z14, stars that fused hydrogen into helium and heavier elements, then scattered those elements into space when they died. And on the deepest level, all of it traces back to the Big Bang, the beginning of space and time itself. MOM Z14 represents one step in that cosmic journey. It's not the beginning. That's the Big Bang. And it's not where we are now, modern complex galaxies like the Milky Way. It's an intermediate step, a snapshot of the universe when it was learning how to build galaxies, when it was creating the heavy elements that would someday be necessary for planets and life. Without that step, without galaxies like MOM Z14 doing the hard work of converting pristine hydrogen into enriched matter, the later universe couldn't have unfolded the way it did. So in a very real sense, you owe your existence to galaxies like MOM Z14. Not this particular galaxy necessarily, but galaxies like it that existed throughout the early universe, forming stars, creating elements, and seeding space with the raw materials for everything that came after. That's your cosmic ancestry. That's where you came from. The observable universe will shrink, not because the universe itself is shrinking, but because fewer and fewer distant regions will be within our cosmic horizon. In the very far future, perhaps hundreds of billions of years from now, the night sky will look different from how it looks today. Most galaxies will have been carried beyond the cosmic horizon by expansion. Only the galaxies in our local group, bound together by gravity, will remain visible. Astronomers in that distant future, if any exist, will look up and see a much emptier universe than we do. They won't be able to see the cosmic microwave background because it will have been redshifted into invisibility. They won't be able to see distant galaxies racing away from them. They might not even be able to deduce that the universe had a beginning, because the evidence for the Big Bang will have been carried beyond their reach by cosmic expansion. In a sense, we're living in a privileged time. We can still see the distant universe, still observe the cosmic microwave background, still study the evidence of the Big Bang. We can see galaxies like MOM Z14 that show us what the universe looked like in its youth. Future astronomers, in the extremely distant future, might not have access to this information. They'll be limited to studying their local environment, unable to peer back to the beginning of time the way we can now. This makes our current observations all the more important. We're documenting a view of the universe that won't always be available. Every galaxy we catalogue, every spectrum we take, every measurement we make, is preserving knowledge about the cosmos that might otherwise be lost to future generations. MOM Z14 might someday be beyond the cosmic horizon, forever unreachable and unobservable. But we've seen it, studied it, learned from it. That knowledge will persist, even if the galaxy itself becomes invisible. Let's bring this back to something personal. Why does any of this matter to you? You're not an astronomer, probably. You're not building space telescopes or analyzing spectra. You're living your life on Earth, dealing with everyday concerns that have nothing to do with distant galaxies. So why should you care about MOM Z14? Here's why. Because understanding where we came from helps us understand who we are. MOM Z14 represents a snapshot of the universe when it was radically different from today. A time when galaxies were just beginning to form, when stars were burning brightly and dying young, when the chemical elements essential for life were being created and scattered into space. That process, repeated countless times over billions of years, eventually led to the formation of our solar system, our planet, and ultimately, us. You are the product of 13.8 billion years of cosmic evolution. The atoms in your body were forged in stars that lived and died long before the sun existed. Those atoms were incorporated into gas clouds that eventually collapsed to form the solar system. They were assembled into the Earth, cycled through countless geological and biological processes, and ultimately arranged themselves into the complex structure that is you. This is your cosmic ancestry. Every element in your body, heavier than hydrogen, came from a star, somewhere, sometime in the universe's history. Maybe some of those elements came from galaxies like MOM Z14, created in the first few 100 million years after the Big Bang. Understanding MOM Z14 helps us understand that larger story of cosmic evolution, the story that connects the Big Bang to your existence. There's also something humbling about studying objects this distant and ancient. It reminds us of how small we are in the grand scheme of things. The universe is vast beyond comprehension, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. MOM Z14 is just one tiny galaxy among all those countless galaxies, and even it contains millions of stars. Our Sun is just one star among all those trillions upon trillions of stars. Earth is just one planet among whatever unknowable number of planets exist throughout the cosmos. You are one person among billions on that one planet. From a cosmic perspective, you're infinitesimally small. But here's the paradox. You're also extraordinary. You're a conscious being, capable of understanding the universe that created you. You can look up at the night sky and comprehend, at least intellectually, what you're seeing. You can learn about MOM Z14, a galaxy so distant that its light has been traveling since before the sun existed, and you can understand what that means. You can grasp the scale of cosmic time and space, even though those scales are far beyond anything your senses can directly experience. That makes you, in your own way, significant. Out of all the matter in the universe, only a tiny fraction has organized itself into conscious, intelligent beings capable of contemplating existence. You're part of that tiny fraction. The universe is vast and mostly empty, but it has produced you, and through you, it can know itself. MOM Z14 also reminds us that we live in a time of extraordinary discovery. Just a few years ago, we couldn't see this far into the universe's past. The technology didn't exist. Now it does, and we're learning things that previous generations could never have known. You're living through a moment in history when humanity's understanding of the cosmos is expanding rapidly. Every few months, Webb releases new images and discoveries that rewrite our picture of the early universe. This will continue for years to come. You're witnessing this unfold in real time. That's a privilege. Your descendants, centuries from now, will look back at this era as the time when humanity first truly saw the universe as it was in its infancy. You're part of that story. There's also a practical aspect to all this. Studying the early universe, understanding how galaxies formed, learning about star formation and chemical enrichment, all of this feeds into our broader understanding of astrophysics. And that understanding has practical applications. The same physics that governs star formation also governs fusion reactions, which might someday provide clean energy for humanity. The same processes that create elements in stellar cores are being studied in laboratories here on Earth. The technology developed for space telescopes like Webb often finds applications in other fields, from medical imaging to materials science. So, even though studying MOM Z14 might seem like purely abstract science, disconnected from everyday life, it's part of a larger scientific enterprise that does have practical benefits. But honestly, the most important reason to care about MOM Z14 isn't practical at all. It's about wonder. It's about the deeply human desire to understand the world around us, to ask questions about our origins and our place in the cosmos, to seek knowledge for its own sake. This impulse is what makes us human. It's what drove our ancestors to map the stars, to develop mathematics and physics, to build telescopes and send spacecraft to distant worlds. It's what drove the teams that designed, built, and launched Webb. It's what drives astronomers to spend years analyzing data, looking for patterns, trying to make sense of what they're seeing. And it can drive you too. You don't need to be a professional scientist to appreciate the wonder of the universe. You just need curiosity and the willingness to learn. MOM Z14 exists. It's out there, 33.8 billion light-years away, even though we're seeing it as it was when the universe was only 280 million years old. It's a real place. Or at least it was when the light we're seeing left it. It contains millions of stars, possibly planets, who knows what else. It challenges our understanding of how galaxies form. It raises questions that astronomers are working to answer. And you now know about it. You understand, at least in broad strokes, what makes it significant and why its discovery matters. That knowledge connects you to the larger human story of exploring and understanding the cosmos. Let's talk about the name, MOM Z14. The MOM part stands for mirage or miracle, the survey that confirmed the galaxy's distance. The Z14 part refers to its redshift, which is approximately 14. Astronomical names are often like this, encoding information about how or where the object was discovered. It's not a poetic name, like Andromeda or Orion. It's a technical designation. But there's something poetic about the concept behind it anyway. Mirage, or miracle, perfectly captures the question astronomers were asking. Is this galaxy an illusion, a mirage, created by dust or gravitational lensing that makes it appear more distant than it really is? Or is it a miracle, a real object that somehow exists when it shouldn't, according to our models? The answer turned out to be miracle. It's real, it's ancient, and it's challenging everything we thought we knew about the early universe. That tension between mirage and miracle, between illusion and reality, is central to how science works. When you see something that doesn't fit your expectations, your first instinct should be skepticism. Maybe you're misinterpreting the data. Maybe there's a simpler explanation. Maybe it's not as extraordinary as it first appears. But sometimes, after careful checking, after ruling out all the mundane explanations, you're left with something genuinely miraculous. Not miraculous in a supernatural sense, but miraculous in that it reveals the universe is more interesting, more complex, more surprising than your models predicted. MOM Z14 is that kind of miraculous. It's showing us that the early universe was more active, more vibrant, more capable of producing structure than we imagined. And that's wonderful, even if it's also troubling for our theories. So here we are, at the end of our journey, exploring MOM Z14. We've covered a lot of ground tonight. We started with the basic concept that looking far into space means looking back in time. We discussed how the James Webb Space Telescope was designed to peer into the early universe and what it's been discovering. We learned about MOM Z14 specifically, a galaxy that existed just 280 million years after the Big Bang, making it the most distant galaxy ever confirmed. We explored what makes MOM Z14 troubling: its brightness, its chemical enrichment, its compact size, its apparent role in clearing the neutral hydrogen fog of the early universe. We talked about how these characteristics challenge our models of galaxy formation and create a growing chasm between theoretical predictions and observed reality. We considered what this discovery means for our understanding of cosmic history, for the timeline of events from the Big Bang to today. We discussed the technology that made this discovery possible and what future telescopes might reveal. And we connected all of this back to you, to why you should care about a galaxy 33.8 billion light-years away. The universe is vast. 13.8 billion years old, 93 billion light-years across in its observable extent, filled with hundreds of billions of galaxies. Earth is tiny within that vastness, a small planet orbiting an ordinary star in an ordinary galaxy. You're one person on that tiny planet, living for a brief moment in cosmic time. And yet, you're capable of understanding MOMZ-14. You can comprehend, at least conceptually, what it means for a galaxy to exist 280 million years after the Big Bang. You can grasp why astronomers are troubled by its properties. You can appreciate the vast distances and timescales involved. That's remarkable. That's what makes us special as a species, our ability to look up at the stars and figure out what we're seeing. Our ancestors didn't have that knowledge. They looked at the same night sky, but couldn't know what those points of light really were. They created myths and stories to explain the heavens, but they couldn't measure distances or ages or chemical compositions. We can. We've built instruments like Webb that extend our senses far beyond what evolution equipped us with. We've developed mathematics and physics that let us decode the messages carried by light across cosmic distances. We've built a framework of knowledge that connects the smallest particles to the largest structures in the universe. And we're still learning. MOMZ-14 is teaching us that we don't have all the answers yet. There's still mystery in the universe, still phenomena we don't fully understand. That's exciting. That means there's more to discover, more to learn, more opportunities to push the boundaries of human knowledge. The troubling questions raised by MOMZ-14 will eventually be answered. Maybe not this year, maybe not next year, but eventually. Some brilliant scientist or team of scientists will figure out what's missing from our models. They'll realize what factor we haven't accounted for, what process we've misunderstood, what assumption needs to be revised. And when that happens, our understanding of the universe will leap forward again. That's how science progresses, through cycles of observation, prediction, confusion, and eventual insight. MOMZ-14 represents the confusion part of that cycle. The insight is still to come. But it will come because the universe operates according to consistent physical laws, and those laws can be understood by beings like us who are patient and clever enough to figure them out. So, what should you take away from tonight? First, the universe is stranger and more wonderful than we realized. Just when we think we have it figured out, it surprises us with galaxies like MOMZ-14 that shouldn't exist, according to our models, but do exist anyway. Second, we're living in a remarkable time for astronomy. The discoveries being made right now will be remembered centuries from now, as the moment when humanity first truly saw the infant universe. Third, you're connected to all of this. The atoms in your body came from stars, some of which might have existed in galaxies like MOMZ-14. You're part of the cosmic story, a local increase in complexity within the vast tapestry of the universe. Fourth, there's still so much we don't know. MOMZ-14 raises questions that challenge our deepest understanding of how the universe evolved from the Big Bang to today. Those questions will drive astronomical research for years to come. And finally, this all matters because understanding where we came from helps us understand who we are. We're not separate from the universe. We're part of it. We're made of it. We're the universe's way of knowing itself. And that's worth celebrating. Thank you for joining me on this journey across cosmic time and space to explore MOMZ-14, the galaxy that shouldn't exist, but does. The galaxy that's challenging everything we thought we knew. The galaxy that's teaching us that the universe is still full of surprises. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep explorations of space and our place in it. And remember, the next time you look up at the night sky, you're not just seeing stars. You're seeing, across light years and billions of years of cosmic history, you're seeing a universe that's vast, ancient, and still full of mystery. You're seeing home. Sleep well tonight, knowing that out there, 33.8 billion light years away, there's a galaxy that has astronomers questioning everything. And thanks to instruments like Webb, we're just beginning to understand what it's telling us. The universe is enormous. MOM Z14 is impossibly distant. But we've seen it, we've studied it, and we've learned from it. And that makes us, in our small way, cosmic explorers. Good night, and keep looking up.